To begin this unit, we're going to have a look at exponents. What I've written here is 4 to the power of 5, or 4 to the 5th. This number 4 here is called the base. The little 5 hanging out top is called the exponent. The meaning of this exponential expression, 4 to the 5th, it means 4 times itself 5 times. So I've written here 4 times 4 times 4 times 4 times 4, 5 times. I've multiplied 4 by itself, and that result is 1024. If you're looking to do an exponent, if you're looking to evaluate it in a calculator, the calculator button might look like this, or it might look like this. To use one of these calculator buttons, this is the one I believe that is in Google Calculator. You would type 4, press this button, type 5, and then press equals, and you will see that the result is 1024. There are some other types of exponents that we will come across. That is a negative base, okay? So this -2 is in parentheses, and the 3, the exponent, is applying to all of that, the negative included. So we're going to take this -2, multiply it by itself 3 times, and our result will be -8. Some interesting things happen when we take exponents of negative numbers, as demonstrated here. -1 to the power of 4, -1 times itself 4 times. You'll remember that a negative times a negative equals a positive. So we've got 2 pairs of negatives here, this pair multiplied and this pair multiplied. So these negatives cancel each other out, and these negatives cancel each other out, resulting in the positive number 1. So there are some rules that result from this. -1 to any even exponent is 1. Those even numbers allow the buddies or the pairs to cancel each other out. -1 to any odd exponent is -1 because there's always going to be one factor left without a buddy to cancel out his negative, resulting in a negative evaluation, a negative answer. Some other things to keep in mind: 1 to any exponent is 1 because 1 times itself, however many times you like, is always going to give you 1. And 0 to any exponent is also 0. You'll see here 0 squared, 0 times 0 is 0. There is one exception to this, and we will talk about that here in this last example. But I want to look at this one first. 7 to the power of 1 equals 7. Any number to the exponent 1 is itself. 7 times itself only one time, okay? There's no multiplication that has to happen. It's just 7. So 10 to the power of 1 is just 10. That's how the power of 1 works. How about raising things to the power of 0? This one's kind of a funny one. 2 to the power of 0 equals 1. In fact, anything to the power of 0 is 1. 1 is the multiplicative identity. That is why this is true. Here's where the funny exception comes in. You'll notice I've written here non-zero. Any non-zero number to exponent 0 is 1 because we list 0 to the power of 0 as undefined. So if you're walking down the street and someone asks you what 0 to the power of 0 is, you tell them it's not a real thing. It's undefined. There is no answer to that problem. So far, we've seen negatives in the base of an exponential expression. Next, I want to look at what happens when you have a negative in an exponent. A negative exponent actually changes the expression into a fraction. Well, I shouldn't say it changes it. It's just another way of expressing a fraction. So 5 to the power of -2 is the same as 1 over 5 to the power of 2. Once you've moved this exponent to the denominator of its 1 over fraction, that negative goes away. Okay, this works as well even if you have a variable in your base. M to the power of a -5 is 1 over m to the 5th. Same thing is true even if we also have a negative in the base. -4 to the power of -2 is equal to 1 over the base, -4 to the power of 2. Whenever possible, we like to write exponents in their fraction form instead of the negative exponent form. So if, as you're working through problems in the next few slides or problem sets, you're resulting in answers that have a negative exponent, we typically do go that one step further and put that negative exponent into its fraction form. Hopefully this idea of negative exponents to fractions is familiar to you. If not, I have a deeper explanation and some intuition on why this works in the supplemental links that accompany this page. In this unit, we're also going to get some practice doing operations with these exponential expressions. So this next page talks about products and quotients of exponents that have the same base, meaning that the base in each exponential expression is the same number. So here you have 2, that's the base, to the power of 3, times 2, that's also the base, it's the same, to the power of 4. If we want to multiply these, the process is actually very simple. When you multiply exponents that have the same base, you simply add the exponents and keep the base. So 2 to the power of 3 times 2 to the power of 4 is equal to 2 to the power of 3 plus 4, or 2 to the power of 7. The same process works even if you have crazy looking variables in your base. As long as the base is the same in both exponents that you're both exponential expressions that you're multiplying, you can follow this procedure. W to the power of negative 5 times W to the power of 3 is equal to W to the power of negative 5 plus 3. We've just taken these exponents and added them together, and that results in W to the power of negative 2. Now remember, in our last slide, this is not the preferable way to present this expression, so we will change it to its fraction form, which is 1 over W to the power of 2. If we can take a product of exponents, we can also divide exponents or take a quotient. Multiplication and division are related. They're kind of opposites in some sense. So if when you are multiplying these types of exponential expressions, you add the exponents. When you divide exponential expressions with the same base, you subtract the exponents. So here, 2 to the 5th divided by 2 to the 3rd will result in 2 to the power of 5 minus 3. What I've done here, I've noticed that the bases are the same. I've simply subtracted the exponents, 5 minus 3, and kept that base, kept the 2. 2 to the power of 5 minus 3, 5 minus 3 is 2. This is 2 squared, also known as 4. Let's try another one. This one has a variable in it, so it looks a little funny. It's also got a negative exponent. Let's see what's going to happen. X to the power of 2 divided by x to the power of negative 3. Well, the base is the same. I can just subtract these exponents. So 2 minus negative 3. Here I've written it out. I've kept our base. 2 minus negative 3. Well, minus a negative, that's the same as adding. So x to the power of 2 plus 3, that's the same as x to the 5th power. If this adding and subtracting with negatives is throwing you for a loop, it may have been a long time since you've done that type of arithmetic. Please check out the supplemental links. I've attached some especially for that prerequisite knowledge if you need some catching up. Don't be afraid to write out each and every step if you need to. You can use a calculator to help you with your positives and negatives, your addition and subtraction with those types of numbers. Also, just be careful with your parentheses. So with something like this, it is always good to keep in mind where your negatives are and to keep your negative numbers in parentheses. It can't hurt, even if they're unnecessary in certain cases. Another operation we can do with exponents is we can take exponents of other exponents. So we can layer exponents in this way. This first example says 2 to the power of 5th, 2 to the 5th power, 2 to the power of 5, and we're raising that whole thing to the power of 3. What happens here is your exponent that's being raised to another exponent, those two exponents are going to be multiplied together. So this is equal to 2 to the power of 5 times 3, also known as 2 to the 15th power. Let's try another one that looks a little bit more scary. X to the power of 4, that whole thing is raised to the power of negative 3. All you do is you keep that base and you multiply these exponents. 4 times -3 gives you -12. X to the power of -12 is your solution. But remember, we want to put this in its fraction form. So this becomes 1 over x to the 12th. Let's look at one more, w to the power of 8, this whole thing raised to the power of -2. Once again, I'm going to keep that base w, and I'm going to multiply these exponents. 8 times -2, I've written out here, that's the same as w to the power of -16, which is equal to 1 over w to the 16th. This next page addresses what happens when you have an operation such as multiplication or division going on within the base of the exponential expression. So you'll see here we have 3x. There's multiplication going on between these two guys right here, 3 times x. That whole thing is being raised to the second power. So what happens here? Well, we have multiplication on the inside here in the base and an exponent on the outside. What happens is this exponent applies to both of the factors. So we can distribute this 2 to the 3 as well as to the x. So 3x to the power of 2 becomes 3 to the power of 2 times x to the power of 2. This 2 just gets distributed among each factor in the product, and it results in 9x to the power of 2. Let's look at another one that has a scary looking negative in the exponent, but it's not so bad. 2w, that's 2 times w, multiplication going on in the base, raised to the exponent -3. This -3 will distribute in the same way as before to that 2 and also to the w. So we have 2 to the power of -3 times w to the power of -3. Remember, we want this in its fraction form, so 2 to the power of -3 becomes 1 over 2 to the third power, and w to the power of -3 becomes 1 over w to the third power. These guys are multiplied here, so they're still multiplied here. Okay, when you're multiplying fractions, multiply across the top. 1 times 1 is 1. Multiply across the bottom. 2 to the third power times w to the third power. Here we are multiplying. Once again, these guys just get stuck together. Okay, they've got different bases. 2 to the third power is 8. W to the third power, nothing we can do with that. That just stays the way it is. Our result is 1 over 8 w to the third power. These examples demonstrate how exponents distribute over multiplication when we have multiplication in the base, and actually a very similar thing happens when we have division in the base of an exponent. So in this next example here, we have 3 over x, and that whole thing is raised to the second power. This 2, this exponent, will distribute over division. It will apply to the 3, and it will also apply to the x. So you take this exponent and you stick it to both pieces that's going on in the division here. So we're left with 3 to the power of 2 divided by x to the power of 2, which is 9 over x to the power of 2. To look at another one, we have w over 5, so there's division going on in the base, an exponent on the outside. We can distribute that exponent 3 to the w and also to the 5, leaving us with w to the power of 3 over 5 to the power of 3. This is equal to w to the power of 3 over 125. For our final page in this topic, what I'd like to do is to show you some problems where we take all of these rules and properties and stick them together in one math problem that we would like to simplify. So I have a number of examples here that combine all of the things in the other slides, and you can use multiple rules and properties at one time. In this first one, we've got a couple of things going on, 12a to the 7th over 2a to the second power. We have, first of all, everything on the top of the fraction is multiplication or an exponent, same thing with the bottom. Notice that this 7, it is applying to the a, but not to the 12, okay? The 12a is not in parentheses here. That means the 12 is standing on its own on the outside, and the a is raised to the seventh power. Same thing in the denominator. The 2 is hanging out by himself, okay? He's not raised to the second power, only the a is, because we have an absence of parentheses here. So I have a 12 on top and a 2 on the bottom. There's nothing stopping me from simplifying that. 12 divided by 2 is 6. So that's the first thing I can do. A to the 7th over a to the 2nd. Well, that's division of exponents that have the same base being a. When we have this case, we subtract the exponents and keep the base. 7 minus 2 is 5, and we keep that base a. Our result is 6a to the power of 5. In this next example, we have a whole bunch of stuff going on. 4x to the power of 8, that's in parentheses. The whole thing is raised to the third power. And 2x to the power of 5. Well, let's see. Let's deal with this part first. 4x to the power of 8, this whole thing is raised to the third power. Remember, when we have exponents raised to exponents, actually, we won't be dealing with that exponent raised to an exponent yet because we have to distribute this 3 over the multiplication that's happening inside here. We have 4 times x to the power of 8. This whole thing, which has some multiplication, is being raised to that third power. So I'm going to take this 3, distribute it to the 4, and also distribute it to the x to the power of 8. 4 to the power of 3, I'll write that here. X to the power of 8 to the power of 3. That's where we have our exponent raised to another exponent. When we have that, remember, you multiply those exponents and keep the base. 8 times 3 is 24. I'll write that here, and I'll keep that base x. Okay, so I've kind of dealt with this third power on this first piece. Let's see, I have this 2x to the power of 5 left over, multiplied by everything. So I'm going to write that over here. From this point, I have this whole thing in parentheses multiplied by this whole thing in parentheses. Let's deal with this 4 to the third first. I know that that is 64. So I will write that this way to kind of have a look at this. So I have just numbers on the outside. I've rewritten it here. 64 times 2. Everything here is just multiplied in a row. We can move this multiplication around, do it in any order that we like. 64 times 2 is 128, and x to the 24th, x to the 5th. This is multiplication of exponential expressions with the same base x. When we multiply with the same base, we simply add the exponents together and we keep that base. So 24 plus 5 is 29, and we keep that base x. So you can see things get a little bit complicated here. It will probably take you some practice to get used to seeing when to apply which rule and how to combine which pieces of the problem that you're looking at. Let's have a look at the next one. A to the power of 7, b to the power of 6. This whole thing is in parentheses, and it's multiplied by this whole thing. A to the power of 3, b to the power of 5. Well, this is multiplied by this, multiplied by this. Multiplication is happening everywhere, so I can do this multiplication in any order that I like. A to the 7th times a to the 3rd. Multiplication with the same base, a. 7 plus 3 is 10. Okay, I can do a similar thing. B to the 6th, b to the 5th. Multiplication with the same base. 6 plus 5 is 11, leaving me with a to the 10th, b to the 11th. This next example here involves a fraction and some negative exponents. 1 over u, a variable, to the negative 8th. Well, this one is very interesting, right? If I ignore this 1 over for a second and I just look at u to the negative 8th, well, I know that that can be converted to a fraction itself. That is 1 over u to the 8th. So I can kind of replace this denominator, the bottom of the fraction, with what I know it is, which is also another fraction. So 1 over u to the negative 8th is actually equal to 1 over u to the 8th. Okay, that looks very scary. If it's been a really long time since you've seen a complex fraction, I've included a link that will help you get familiar with that. You might see this on rare occasion in other problems coming up in the course. But 1 over, well, that just undoes the 1 over. So 1 over u to the 8th is simply u to the 8th. There's a number of ways to see that when you convert division to multiplication, but remember division and multiplication undo each other. You can't 1 over again. That fraction goes away when you do that operation, leaving you with just u to the power of 8. Again, if you need some catching up on complex fractions, have a look at the supplemental link. Okay, this next one has a bunch of things going on. I see a negative exponent. I also see a bunch of multiplication raised to an exponent. So 5a to the negative 4th, b to the 3rd, this whole thing raised to the 3rd power. Well, I can't really do much of anything with what's in here. I mean, I suppose I could take care of that a first if I wanted to, but this exponent out here is bothering me, this 3 out here. I have multiplication inside. This whole thing in the parentheses is a base, and here's an exponent. I know that this exponent can distribute over the multiplication in the base. So I'm going to apply this 3. I'm going to distribute it to the 5, to the a to the power of negative 4, and also to the b to the power of 3. Okay, so I have 5 to the 3rd power, distribute that 3 to the 5, and then I have a to the negative 4th, that 3 distributes here as well. So I'm raising a to the negative 4th to another exponent, which means multiplying by that 3. Same thing's happening with b to the 3rd. I'm raising that to the 3rd power. When you raise an exponent to an exponent, you multiply the exponents as well. So that leaves me with this kind of intermediate step here, multiplying these exponents and that 3 that's also applied to this 5. 5 to the 3rd power is 125. A to the negative 4 times 3 is a to the negative 12. That should be a 2 there. I left out my 2. And b to the power of 9. 3 times 3 is 9. This results in 125 b to the 9th over a to the power of 12. Remember, we want to change that negative exponent so that it is in its fraction form. Next, we can have a look at this wild fraction here. 2t, that's our variable, to the power of 5. Notice 5 is only applying to the t, not to the 2, because we don't have parentheses here, over s to the power of negative 2, u to the power of negative 3. Okay, well, I want to take care of these negative exponents. Each one of these can be turned into a fraction form. S to the power of negative 2 is 1 over s squared. U to the power of negative 3 is 1 over u cubed, to the power of 3, throwing out terminology I haven't defined yet, I apologize. These guys are just multiplied here, so they're just multiplied here as well. S to the power of 2 times u to the power of 3, those guys just get stuck together. 1 over. Here again we have a complex fraction situation going on, so something over 1 over kicks these guys on the bottom right back up to the top. We have 2t to the power of 5, s to the power of 2, u to the power of 3. And in our final example for this page, let's see, we have a fraction, a to the power of 2 over negative 4, b to the power of 7, and this whole thing is a base raised to the exponent 8. Now I have division in my base, so I can distribute this 8 to the top and the bottom of that division. When I distribute it to the top, well, I have a to the power of 2 raised to another exponent, so I'm going to multiply those exponents. When I distribute this 8 to the bottom, it's distributing to the whole bottom, okay, the whole thing. So this 8 has to then distribute over the multiplication in the bottom. The 8 distributes to the negative 4 to the power of 8. The 8 also distributes to the b to the power of 7. That's b to the 7th raised to another exponent, so we multiply those exponents, b to the power of 7 times 8. And if I kind of clean up some things here, 2 times 8 is 16, a to the 16th, and on the bottom here, negative 4 to the power of 8. Oh, that's crazy looking. It's this really big number here, and b to the 7 times 8. That's b to the power of 56, a very big power there. In your first assignment, you'll have lots of opportunity to practice these types of problems. Use all of the helpful resources available to you in Math Excel to work through these problems and get some practice and some intuition into how they work. And of course, if you're struggling, reach out for help through any of the Moodle communication features, either to the entire class, someone may have a very similar question in the open discussion forums, or through any communication with me through Moodle or email as well. Good luck!